the last thing I want to discuss in terms of numerical methods is error bounds. So what these are a bound on the largest possible error that you can have from your scheme. And you can see just from looking at the form of it, okay, that for example, for our midpoint and our trapezoidal rule, the error goes as 1 over n squared, whereas for Simpson's rule, the error goes as 1 over n to the 4th, okay? So obviously Simpson's rule is better because you just are going to get a lower error, right? So that's one thing that you can just see from these things here. The b minus a, of course, is the length of the interval. N is there. You've got a number here, some number in the bottom that comes from the error bound, and how you got the error bounds. And then you've got this k here. K is on midpoint and trapezoidal rule. K is the maximum size of the second derivative. And for Simpson's rule, k is the maximum size of the 4th derivative, okay? And it's not a surprise, actually, that it's n squared and second derivative, n to the 4th and 4th derivative. In fact, we don't quite have enough mathematical machinery to prove these yet, but you will by the end of this class. So I'm just going to skip the proofs, but if after we've done some series and stuff, you want to go back and figure out how these things get proved, you'll be able to do that by the end of the class. In any case, right now I just want to use these formulas. How do we figure out how to use them? Well, let's just do our example. Now, these can be a pain to do. It's not conceptually difficult, but you see, what you have to do is you have to take the second derivative or take the 4th derivative and find the maximum on the interval. So how do you find the maximum on the interval? Well, you can then, take another derivative, set it equal to 0, find the maximums and minimums, and check the endpoints using the closed interval test. Or you can do a graphical method. I'll allow that if you come up with the derivative and then use a graphical method to find the maximum. For something fairly simple, that's not hard, right? Taking a couple derivatives and finding the maximum. But for most functions that we would actually need to do a numerical method because we can't take the integral analytically, probably it can get kind of nasty to take successive derivatives as well. So it can be a little harder. So I'm going to do an example where we can figure it out without too much difficulty. The example that we had before, integral from 1 to 3 of e to the 1 over x dx. So with n equals 8, that's what we did in the previous video. Oh, I can't see the top there. There, now we can see it. But that's the one we did in the previous video. Now we're going to figure out how close our error was. Okay? Right. Let me put a bar here so we can figure this mess out. So I have to take, let's do midpoint and trapezoidal first. I have to take 2 derivatives. Doesn't seem too bad, right? E to the 1 over x. The first derivative, though, of course, all these are going to be chain rule, right? So my first derivative is this, minus x, 1 over minus x squared is 1 over x. Now I have to use the power rule. I meant the other one. Product rule, right? So I've got this times the derivative of that. Well, it's another one, right? So it's going to be this plus this times, plus this times the derivative of this, right? So I will get plus 2 over x cubed, right? Okay, so that's my second derivative. Now, if I were to do the closed interval test, I have to take the third derivative and look for the maximums and minimums. So where the third derivative is 0. So let's check that out. So the third derivative, let me, maybe move it over here to have a little bit more space. Okay, so I'm going to get this thing times negative 1 over x squared e to the 1 over x plus the derivative of this guy. So this would be minus 4 over x to the 5th minus 6 over x to the 4 e to the 1 over x. That's an x5 here. So if I kind of collect these, that times is going to be minus 1 over x to the 6th, and then there's 5 to minus 6 over x to the 5th minus 6 over x to the 4. Okay, so remember, I'm interested in what's happening on my interval, which is 1, 3. So I could try to set this equal to, I would do a bit of work, right, to set this equal to 0 and see if I can get it equal to 0 anywhere. But I can tell you what, I can also just sort of look at this. Notice that on my interval, everything here is positive, right? It is going to all be positive. All of these things are going to, all the x's are going to be positive. So all these negatives is going to make this whole thing negative, right? E to the 1 over x is always positive. So the third derivative here is purely negative. That's telling you then the second derivative is decreasing. So I'm not going to have any maxes or mins. So I could do a little bit of work, or I could visually, if I put this into Desmos and drew this, I could see that it's going down. Okay? So second derivative is decreasing, always decreasing. I'm not going to get any maxes or mins in my interval. So my maximum is going to happen at the endpoint, okay? So that is going to be, let me see, these are all, let me see, I want to keep this guy because I need to take another derivative, okay? So maximum is at x equal 1, right? So the second derivative at 1 is going to be 3e. So that's my k1, the maximum value of the second derivative on my interval. Okay? Leave that there. All right, so that means that if I go back to these and put in what I have, the maximum error for the midpoint rule is less than or equal to 3e times b minus a, which is 2 cubed over 24 times n, which was 8 squared, right? So where did I work this out? Where I worked this out here somewhere. Midpoint rule, 0.0425. And then for the trapezoidal rule, and this is a maximum. Your actual error might be less, but this is a theoretical maximum. Okay, so this one turned out to be 0.0849. And that's sort of a thing that we can discuss real briefly here. You might think that the trapezoidal rule is better than the midpoint rule because you are using a trapezoid. But it turns out, if you look at it, the midpoint rule is a little bit better. Because when I look at, say, a curve, okay, so here's the curve, here's that. But if I'm taking the midpoint, it's actually like a little bit above. So I do have My overshoot and undershoot is a little bit better because it would be down here. You know, if it was basically, if you thought about it from the trapezoidal rule standpoint. So they're on the same order, right? In other words, they behave the same way with the n squared in the bottom, but midpoint rule is a little bit better. But as you saw in our examples, we have to like figure out what the midpoints are. So it was a little bit more annoying in some way that you had to figure out the midpoints. All right, so those are our errors for this particular problem. For midpoint and trapezoidal rule, we now want to also find the error for Simpson's rule. Okay, so we have to take the fourth derivative. I'm going to erase this. My third derivative, I left it on the board here. Okay. And I have to do the same thing. So I'm going to get this, whatever this was. And then I have minus 1 over x squared e to the 1 over x. And then I'm going to add the derivatives here. So this should be 6 over x to the 7. And then 6 times 5 is 30 over x to the 6. And then this would be 6 times 4, so 24 over x to the 5th, e to the 1 over x. Okay, so you can kind of see what's happened here. Similarly to what we saw before, this one was always negative. Because of the signs, these are going to be all positive. And what do I have? 1 over x to the 8 plus 12 over x to the 7 plus 36 over x to the 6 plus 24 over x to the 5th e to the 1 over x. All right, so now I would take the derivative of this again. I'll write this as a 4 so I'm consistent with what I have written over there. I would take the derivative of this again and then see where that's equal to 0. Because I'm looking for the maximum value of this fourth derivative on this interval. Okay, but because I don't want to make this video 20 minutes long, I'm going to tell you what happens. The same thing happens, and you can see what happens. You can see why, right? When I take the derivative of this again, when I do this guy times this one, the derivative here gives you a minus, so all of those are minuses. And then when I take the derivative of this, each of these minuses goes down, right? You're multiplying by the negative, so the whole thing is going to be negative. And we don't really care what the numbers are. We can figure them out. But the important thing is that, like we saw with the second derivative, the fifth derivative is always negative, which means that the fourth derivative is a decreasing function. And of course, by always, I mean, well, for all positive x's, right? I don't know, because if I've got some negative x's, some of these things might be negative, and I don't know. But I also don't care, because I really only care about the interval from 1 to 3. Okay, so if it's decreasing, then the maximum has to be, again, at the left endpoint, which is at 1. So then I do f4 at 1, which is then, if I put this in here, I'm going to have 1 plus 12 plus 36 plus 24e, right, which is what? 72, 73, 73e. Okay, that's my K2. Okay. So, almost done. I just have to now put that K2 into my Simpson's rule, error bound, to come up with this number. We're going to get rid of that. I'll leave that at least so that it's explained there. So the maximum value of this Simpson's rule, this is going to give me 73e. 2 is b minus a to the 5th. And then I've got 180 times 8 to the 4th. And I wrote this down too. 0.00861. So you see we got another, our other ones were 0.08 or 0.04. So we have another decimal spot here. We got another significant digit. So that is really good. At least we can say what we had worked out in the previous video for our S8. We had 3.5224. So at least we got the 3.52 going there. We know that that is right. So that is that. I do want to mention one more thing. You don't want to forget, because these were all positive values. You don't want to forget these are absolute values. So absolute value of f and absolute value of the second derivative, absolute value of the fourth derivative. So in this case, everything was positive. So you're just going to take the maximum one. If it was going underneath, then you would have to find the minimum, right? And then you would take the absolute value of that. So you do have to be clear. This is also the absolute value of the error, and this is the absolute value of those second and fourth derivatives.